Hello, welcome to this video. This is for Tammy and it's from 2020. I think it's paper 22 and it's question number 3. Question 3, October, November 2020, and it's paper 22. All right. So PCl3 is used to convert alcohols to chloralkanes such as T. There's T. A possible synthesis of T is shown. Identify a reagent that could be used for reaction 1. So what's happening in reaction 1? Well, this carboxylic acid group has turned into a primary alcohol. And to do that, it is a reduction. And for carboxylic acids, to reduce the carboxylic acid, we need lithium, aluminium hydride. Okay, or LiAlH4. You can't use the other one. What's the other one? Sodium borohydride. It's not a strong enough oxidizing agent. So there you go. That's the first bit. Explain why the term. Explain what is meant by the term optical isomer, and circle any optical isomers there. All right. Now, first of all, let's have a look for the optical isomers. It's got to be a carbon atom. So this one is not. This one is not, because there's two CH3 groups on this, so this one is not. This one is not. This one is. This one is not. So this is the optical isomer. Now, what is an optical isomer? You just a nice short definition of this. It's a molecule with a non-superimposable mirror image. Okay, that's a good definition of an optical isomer. In other words, there's two things. It's their mirror images of each other, and the mirror images they can't be superimposed on each other, like your left hand and right hand. Okay, they look kind of the same, but they're mirror images, but they can't be superimposed on each other. All right. Okay, that's what an optical isomer is. T is a minor product in the reaction. Let me move this up. T is a minor product of the reaction in the reaction of compound S with HCl. Draw the structure of the major product. All right, so let's have a look at this. I'm going to draw this thing first of all. There. Okay, so what we're doing is we're adding HCl, and HCl looks like this. And obviously the HCl is going to go across both double bonds. So the H is going to go first because it's delta positive, and the chlorine is going to go on second. Now, which side is the H going to attach to? That's the thing. Now, it's going to attach to the carbon with already more carbons attached. So it's going to attach to this carbon, the H is. Okay, so the H is going to go there, and therefore the Cl is going to go there. Okay, so let's get rid of that double bond. Let me redraw that. The Cl is going to attach there, and the H is going to attach here. Same's going to happen on the other side because of Markovnikov. All right, the H, wrong color, but never mind. The H is going to attach to this carbon. All right, and the Cl to this one. Now, I haven't drawn that nicely, so I'll redraw that again. It's going to look like this. There's going to be a Cl there, and that thing, and a Cl there. All right, and that's what's going to happen because the double bonds were here and here, and now they've gone. Okay, so that's what you get. All right, and that's the answer. All right, let me look at the other one, and I'll get straight back to you. Okay, this is the second one Tammy asked about. This is paper, or let me do it properly. This is 2019, paper 42. Sorry, paper 22, and it's October, November. October, November, paper 22, 2019. All right, and this is question 4B. All right, let's have a look at this. Phenol reacts with steam to form a mixture of three isomers. Oh, prenol. Gosh, that was it. Phenol. Prenol reacts with steam to form a mixture of three isomers, J, K, and L, of molecular formula that when J is heated with excess acidified potassium dichromate, it forms an organic product which shows no reaction with 2,4-DNPH. Draw the structure of J. Oh gosh, I think we've missed out an earlier bit of the question, haven't we? So let me mess around here. Let me turn this off. Okay, there we go. I found the prenol. The reason I was worried there is because phenol is in A2, and I honestly thought it meant phenol. This is phenol, okay, which isn't on our syllabus. This is A2 stuff. But this is prenol, so it's not the same stuff at all. So prenol reacts with steam to form a mixture of three isomers, that, and that, of molecular formula that. When J is heated with an excess of acidified potassium dichromate, it forms an organic product which shows no reaction with 2,4-DNPH. Draw the structure of J. Well, I think the first thing we've got to do is draw the three isomers first. Okay, so I'm going to draw this prenol here. CH3, CH3, double bond, CH, CH2, OH. And we're reacting with steam. So let's get my steam here. Steam is H and OH. Now, I'm assuming what happens here is the H goes on one side and the OH goes on the other side. So my first guess at this is going to be this. I'm going to put the OH on here, and I'm going to put the H on here. All right, I don't know which isomer this is, but I'm going to guess it's one of them. Okay, so let me try it again. CH3, CH3, CH, CH2, OH. And now I'm going to guess the opposite. So I'm going to put H here and OH here. Okay, now they're the only two options, aren't they? Yeah, if you think about it. All right, they're the only two options, but it says we get three isomers. Okay, where does it say three? There it goes. So you get three isomers. I'm going to get rid of my prenol over there. Put it over there for now. You said you get three isomers, and I've only found two. Now, and this is a general rule in chemistry. If you can only think of two things, if you can only see two isomers, well, then you've got to look for weird isomerisms. Okay? And the one I can think of here is optical isomerism. Now, does this one show optical isomerism? It does not. But this one does. This one does not. But this one does. So there's going to be two of these, two isomers of this. Okay? And they're going to be optical isomers of each other. Okay, so we found the three. When J is heated with an excess of acidified potassium dichromate, it forms an organic product which shows no reaction with 2,4-DNPH. All right, now if it shows no reaction with 2,4-DNPH, it means there is no carbonyl in the oxidative product, in the product of oxidation. So let's go through these, shall we? Right, we have to oxidize it with acidified potassium dichromate. All right, this is a secondary, what is it? No, it's not actually. This is a tertiary OH group. So nothing's going to happen to this. Let's have a look. This one, excuse me, is going to form the carboxylic acid. Sorry, I've got a bit of a cold, as you can probably hear. So this will not react with 2,4-DNPH. Well, so I'm guessing this is the oxidative product of J. This is not J. This is the oxidative product of J. Okay? Now, let's have a look at the other one. Well, if I react this with acidified potassium dichromate, this bit's going to form my carboxylic acid, and this is what is it? This is a tertiary alcohol again, and this will not form. Is it? No, it's a secondary, isn't it? Because there's an H there. Sorry about that. My cold is getting the better of me. So this is a secondary. So this will form a ketone. So both of these optical isomers will react with 2,4-DNPH. Okay, so that's quite complicated. I must admit, there's a lot going on there. But let's have a look at it. When J is heated with excess acidified potassium dichromate, obviously that's going to oxidize things. It forms an organic product which shows no reaction with 2,4-DMPH. So this is the oxidative product, but it doesn't want that. It wants J. So we've got to backpedal a bit and try and remember what J was. So J, let me get rid of all this now. Taking a while. Okay. It's a tricky question, I must admit, because there's a lot. Chemistry is like that. It often asks for double negatives and sort of stuff. So if you remember, J was this. CH3. CH3 with an OH there. And a CH. H. CH2OH. This must be J. Okay? Because its oxidative product will not react with 2,4-DMPH. I hope that makes sense. It's very, very confusing, I must admit, but there you go. All right. So, where are we now? So, I think we're good there. That's the first bit done. All right, so let's move up a bit. K and L are stereoisomers, which we knew, didn't we? Yeah. Now, I've done the thing with J. Whoopsie daisy. Let me pick this. Oh, it's not letting me do that, is it? Let me try and get rid of all this stuff. Okay, and oh, it's not working, is it? It's annoying when it does this. Microsoft Whiteboard isn't the easiest thing to use. All right, it's not very good at manipulating things. I think there are other things out there that are better, but I'm used to this now. All right, and it works nicely with Screencastify. All right, so we've got all rid of this rubbish. And I've just realised I've just destroyed J there, haven't I? So this is J, this is CH3, and this is an H. Now the other two are K and L. Now these were this CH3, CH3. There was an H here, H, and the OH went here, and then the CH2, OH. Now this one is exactly the same. I can't really show it on here, but these two are stereoisomers of each other, even though I've drawn them exactly the same way. Right, but they are. Okay, and if you look at it, this is the chiral carbon. So K and L are optical isomers of each other. Isomers. All right, there you go. All right, so K and L are stereoisomers, which we know, with a molecular formula C5H12O2, which I hope we've got, yeah. K and L both react with heat when heated with acidified potassium dichromate to form M, which is that. M forms an orange precipitate on reaction with 2,4-DMPH. Okay. Right. The K and L react. Oh yes. Give the structural formula for K and L. All right. So I'm going to draw this. It's CH3 twice CH. CH OH CH2 OH. I think that's it. That looks roughly right to me. That's the structural isomer of that and that, isn't it? Then type of isomerism, well, we've talked about that already. It's optical. Let's move this a bit up a bit. Whoopsie daisy. Okay, give the balance equation to represent the reaction of K with acidified dichromate. We can use that. Right, now they've told us what it is. It's C5H12O2, and it's going to give us C5H8O3. Okay, so obviously we're going to get some water off, and we're going to get 3 oxygens from the oxidizing agent. Okay, now these are tricky. Let's go up again. Right, if you look at what's going on here, let me try and chop bits off. This, first of all, is going to lose a hydrogen. So there, and another hydrogen. So it's going to lose 2 hydrogens. There. So we've lost 2 hydrogens. It's going to CH2OH. Let me draw that bit. H2OH is going to lose that bit. But then it's going to gain an O, an O, and an H. So one of those O's is there, one of those H is there, and H2. So how many have we got? 2, 3, 4. We've got 4 H's we've got to mess around with. The so 4 H's are formed. That means you're going to get 2 waters. All right. And each water requires an oxygen. And each one of these requires an oxygen as well. So that's where we get the 3 oxygens from. Excuse me. So there you go. So I hope that makes sense, even though that's quite a hard one. You'll have to mess around with this one to understand it. Mess around with. All right. Prenol contains an alkene functional group. Describe a chemical test to confirm the presence of an alkene functional group. Give the test the result. Well, obviously this is the bromine water. We add bromine water. Okay. And it turns it from brown to colorless. That's what bromine water does. It can be polymerized. Draw a repeat unit of the prenol. There's the prenol there. Let me bring it down. Okay, so let me draw one prenol. CH3, CH3, CH2OH. This is very simple. I'll show you how to do it. You get rid of the double bonds. Draw a line there, draw a line there, and that is the repeat unit. It's simple as that. All right, I hope that helped, and I'll make another one.